Hello APC Mechanics students, today we'll solve the past paper FRQ 2001 exercise number 3. A light string that is attached to a large block of mass 4m passes over a pulley with negligible rotation inertia and is wrapped around a vertical pole of radius r as shown in experiment A above. The pulley here is of negligible rotation inertia, which means the tension here is transmitted to the tension here, and basically negligible rotation inertia means negligible mass. The system is released from rest, which means the initial speed is 0, and as the block descends, the string unwinds and the vertical pole with its attached apparatus rotate. The apparatus consists of a horizontal rod of length 2L with a small block of mass m attached at each end. The rotation inertia of the pole and the rod are negligible. So basically this is the pole and that's the rod. They don't have any rotational inertia. In part A, they're telling us determine the rotational inertia of the rod and the block apparatus attached to the top of the pole. So we need to determine the rotational inertia of the rod and the block apparatus attached to the top of the pole. This is the pole, so basically we need to determine the rotational inertia of the system that consists of two blocks and the rod. Remember that in the text they've mentioned that the rod has no rotational inertia, so the rotational inertia is basically for the two blocks. And we know that the block in this case is considered as a particle, and the rotational inertia of a particle is given by mr square. If this is 2L, then the radius is given by just L. Then the rotational inertia for each one is given by ml square plus ml square, which is the double of ml square. Then in this case, the total rotational inertia of the rod and the block is given by the double of ml square. Now the moment they ask us to determine the rotational inertia, which means that we're gonna use it later in either energy or in Newton's law. And in part B, they're asking us to determine the downward acceleration of the large block, and this is done by utilizing Newton's second law for translation. Now we can directly write the equation, which is given by 4mg minus the tension is equal to 4m multiplied by a. Now in order to solve for the acceleration, we need to determine the tension. The tension again is applied by applying Newton's second law for the pole and the rod and the blocks. So first let me start by saying that apply Newton's second law. Now it's not important to mention whether for rotation or for translation, but here, for example, let me say for the block. And it's given by F naught, which is MA. And basically we have the pull of gravity, the tension, which is 4MA. And now we need to project the following vector equation, then projection. Along the vertical. And the positive direction is down because it's accelerating downward. Then I will say that 4mg minus the tension is equal to 4ma. Now we have two unknowns given by the tension and the acceleration, and in order to determine the tension to get the a, we need to apply again Newton's second law for rotation, but now we're gonna apply it for the system, rod and the block. So now again let me say apply Newton second law and now that would be for the rod and block, and that is given by tau naught is equal to I multiplied by alpha. Now what are the forces that are acting on this rod? So basically we only have the one, which is the tension, and the tension through the string, and basically we know that always tensions along strings are applied tangentially, so no need for cosine. And notice that here carefully the pole has a radius r, so basically the torque produced by the tension is due to a radial distance given by r. So here you might include, for example, the torque produced by gravity or the normal reaction, but we can ignore them. So the torque produced by the tension is equal to the rotational inertia I, and alpha here, because we're considering motion is occurring without slipping, so all the system have the same acceleration and same velocity. Now the torque produced by the tension would be T multiplied by the radius of the pole, which is r. And here you should be very careful. Alpha, what does it represent? Alpha should be related to the acceleration of the system which is rotating. Now here, because we're talking about, so this string and this pole would have the same acceleration, which is a. For this reason, if we need to relate alpha to a, then alpha would be given by a divided by r, in which r is the radius of the pole, because the string is in contact with this pole. Okay, then here I would say that the rotational inertia of the system that we have determined previously is given by 2ml square, and alpha is given by a divided by r. Now in this case, the tension would be given by what? Would be given by the double of ml square divided by r square multiplied by a. Now this tension would be replaced here. So let me say that this is Ft and Ft. So in this case, what do we have? We have 4mg minus the double of ml square divided by r square multiplied by a is given by 4ma. Now we can apply the cancellation effect for the masses, they cancel, and we will move this to the right hand side. So that would be 4g is given by 4a plus the double of L square R square multiplied by A. Reading the equation from right to left and factoring A, that would be 4 plus the double of L square divided by R square is equal to 4G. And indeed the acceleration is given by 4G divided by 4 plus 2 L square divided by R square. Now here you can do further simplifications in the expression. If you notice carefully, you can simplify here by 2, and this would be 1. And here we can do the common denominator, that would be R square, and that would be R square. So another representation would be as I have said so, or you can leave it as it is. Now in part C, they're telling us when the large block has descended a distance d, how does the instantaneous total kinetic energy of the 3 blocks compare with the value of 4 mgd? Check the appropriate space below. Now when this has fallen or descends a vertical distance d, when this goes down a vertical distance d, so they're telling us to compare with 4 mgd if you look at the question. Now what does 4 mgd represents with respect to a mass of 4m and the vertical distance d? This is basically the gravitational potential energy. So this will lose a gravitational potential energy given by 4 mgd. Now if you notice carefully, we have kinetic energy stored in this block, and in this falling block. And as you can notice carefully, none of them except for this one is changing in height. So all of them, they are rotating. Basically what we can say is that the gravitational potential energy lost due to the descending block is completely converted to the total kinetic energy of these two small blocks and the big block. For this reason, we will say it is equal to 4 mgd. Why? Because since the decrease in the gravitational potential energy of the 4m block is 4 mgd, and there are no frictional forces. So basically, you know that frictional forces, they dissipate energy. As long as there are no frictional forces, there is a complete conversion of energy, and there are no frictional forces, then the total kinetic energy of the three blocks is 4 mgd due to complete conversion. And now for the last part of this exercise, they're telling us the system is now reset. The string is rewound around the pole to bring the large block back to its original location. The small blocks are detached from the rod and then suspended from each end of the rod using strings of length L, as shown here. The system is again released from rest so that as the large block descends and the apparatus rotates, the small blocks swing outward, as shown in experiment B above. This time, the downward acceleration of the block decreases with time after the system is released. Now in part D, when the large block has descended the distance d, how does the instantaneous total kinetic energy of the three blocks compare to that in part C? Check the appropriate space below. Now again, we have reset the experiment, and this will fall a vertical distance d, then the loss and the gravitational potential energy is given by 4 mgd. And again, we don't have any frictional forces, so there is a complete conversion of energies. But if you notice carefully, in addition to the kinetic energy stored or converted to these three blocks, two small blocks and one big block, here we have strings attached to the blocks. Initially, before this started rotating, we expect under the influence of gravity, the positions of these blocks would be, or the configuration would be something like this. Now, after rotation, apart or in addition to the kinetic energy that is stored in these blocks, these will elevate upward, which means they will gain gravitational potential energy. Then what we can say about a state's initial and final state, what's happening? Initially, we only have gravitational potential energy due to the 4m block, and this will completely convert it to the kinetic energy of the blocks of the system plus an additional gravitational potential energy due to these two small blocks, because they will elevate. The gravitational potential energy of this block will increase, unlike the previous configuration where these cannot elevate, so the only conversion of energy is due to pure kinetic energy. For this reason, if we're comparing, we should say less, because part of the energy will be given to the gravitational potential energy for these two blocks that will elevate in height. Then here we can say the total energy available is still 4 mg dy, because the block again will descend the same vertical distance d, but while the two blocks rise, they will gain part of this energy as a gravitational potential energy. Then the total kinetic energy of the three blocks must be less than that of part C. And that's it for Mendez Zodi, guys. See you soon in a new one.